Yeah, you are the host now. You can go ahead.
Okay. So shall we start now,
Yeah, we can start.
or shall we wait for some time?
We can wait for like 1 minute or like in
Okay.
meanwhile we can
Okay.
like
By 2 minutes we'll wait. Then we will start.
in meanwhile we can recap the study session and agenda for the today class.
Sorry. Hello.
Well, we can like a review of the study session, what we have discussed yesterday, and
Yes.
what
Yes.
we are going to
Yeah.
discuss
Yes.
today.
Yes. So yesterday we have discussed. Yeah, we started with the load flow studies, and we understood what is the load flow, why we are conducting the load flow studies. That's what we are studying. We have discussed like. The purpose of conducting the load flow studies, one is to determine the component or the circuit loadings, which we have simplified it as the equipment loading. And second one is to find out the steady state bus voltages. So in addition to the steady state bus voltage magnitude, so we have to look into the bus voltage angle, which we will call it as a load angle also, right? So, and we have discussed, right, in India, the relative angular difference between the sending end and the receiving end, or we can call it as an adjacent buses, to which transmission line, to which the adjacent buses which have been connected by a single transmission line or whatever it may be. So the allowed limit of the relative angular difference is 23 degree in India, whereas other countries it is 30 degree. So that's what we have discussed. So today we will continue that session. Okay, right. Now let me share my screen first.
Yeah, okay, thanks.
Yeah. Yes. Let me share my screen. Right. So this is what we are discussing about this load flow studies. Particularly, we are talking on the IEEE 399. Just let me 1 second. Okay, fine. Right. So the very first purpose of conducting the load flow studies is to determine the component of the circuit loading, which we will call it as an equipment loading. Second is to find out the steady state bus voltages, magnitude, and the bus voltage angle. Okay. Then coming back to this, again, the third purpose of conducting the load flow study is to find out the reactive power flows. Unfortunately, the yesterday file has been deleted. I will try to note down the points what we have discussed in the yesterday and share it with you all. Next, the third purpose of conducting the load flow study is to find out the reactive power flows. How we are talking about the real power flow, we need to talk about the reactive power flow also. So this reactive power flow gives 2 or 3 important informations. It decides basically what is the power factor correction requirements. Under the reactive power flow, we can able to find what is the power factor correction that is required that is in terms of the capacitor or the reactive power compensation. That could be either inductive or combination of inductive and capacitance, right? So this also gives an interesting information. What is the loop flow? Loop flow. Any idea what is the loop flow? Anyone have the idea? Have you ever come across this term, your loop flow? Yeah, fine. So see, if you have 2 generators, if you are having 2 generators, what is the power which is flowing within these 2 generators, which is just circulating, but it is not really delivered to the load? That is called the loop flow. And that is also an example of the reactive power flow. So loop flow, especially we will talk about the reactive power flow. So what exactly meant by that is, let's open the paint here. Yeah, let's suppose I'm having 2 generators.
So we can't see your screen.
Screen is not shared, huh?
Yes, sir.
Oh, sorry. Yeah,
Yes.
right. So basically, what is the loop flow? Loop flow is, let's suppose we are having a generator and this generator is connected to the grid, and the same grid we are connected another generator. Okay. Then both are feeding the loads, for example. This is the loads. So here, let's suppose the generator voltage is, for example, 400 kV by 21 kV. And here also the generator transformer or whatever it may be, that rating is also 400 by 21 kV. Okay. Ideally saying, what is the voltage available that this bus, that is 21 kV, right? So in the generators, we are having a function that is called automatic voltage regulator. The purpose of the automatic regulator voltage is to maintain the generator terminal voltage within the predefined limits. Okay. For example, how it will maintain the terminal voltage at the generator, how it will maintain, how the AVR will maintain. In the AVR, you have two functions. One is, it will just like a comparator. Simple terms, if you ask me, it will like a comparator. So two inputs will be go to the comparator first. So one is the U reference. So this is called the U reference. U reference is nothing but your generator set point voltage. For example, your generator rated voltage is 21 kV. So that means 21 kV corresponding to your 100% of your generator terminal voltage, right? So U reference is 100%. That means you have given command to the AVR or the automatic voltage regulator to maintain the generator terminal voltage to 21 kV or 100% of the generator rated voltage. Okay. Then there is another feedback that is called U actual. That means this is the actual generator output voltage. Okay. So how the AVR will function? So this will take, it will compare both the reference value and the actual value. So this U actual is directly taken from the, there is a PT or the potential transformer at the output of the generator, which will be used to measure the terminal voltage of the generator. And through that PT, we will give the input to the AVR, automatic voltage regulator, right? So this U reference is the set point to maintain the generator terminal voltage, and U actual is the feedback that will taken from the generator output. Okay. And when you give the both the inputs to the comparator, it will check the difference. And there is a PID controller, and it will give an output to maintain. It will always try to maintain the generator terminal voltage to, it will always try to maintain the terminal voltage to near about 100%. But unfortunately, it will never meet the 100% because when your U reference and your U actual will same, then there will the PID output will be 0, right? So it will always try to bring back the voltage of the generator to near about 100%. So let's suppose for this generator, I have given the generator set point as, let's suppose 100%. Okay. And for this 100% voltage, let's suppose the voltage is, let's suppose 21 kV ideally. And for this generator, I am giving the generator set point as, let's suppose 105%, or let's suppose 102%. Okay. So what will be the 102 of 21 kV? So this is 21.42, right? So if I say here, this is 21.42 kV is the generator output voltage of this particular generator, whether this generator will try to maintain 21 kV. So if you see here, there is a voltage difference between these two generators, right? So in this case, what will happen? The reactive power will flow in the loop instead of going into the generator, instead of going into the load. Okay. So that means the power which is flowing between these two generators, which is just circulating, it is not really delivered to the load. So that is called the loop flow. Okay. And this is precisely applicable to the reactive power flow. So when you are looking at why reactive power flow is important or why it is an outcome of the load flow, what you need to optimize is, one, from the low voltage perspective, that is like a 3.3 kV, 415 volt, 11 kV, 6 point, etc., etc. You need to decide what is the ideal capacitor bank which is needed to improve the power factor. Okay. So this is applicable for 3.3 or 11 or 6.6 kV, or you can say it as a medium voltage and low voltage systems. So the reactive power flow is required to find out or to optimize what is the capacitor bank which is needed to improve the power factor. Okay. If you talk about the same in the EHV and HV systems, 400 kV or 33 kV, you will call it as a reactive power compensation. Okay. So the terminology is the technical concept is same in both the cases, but in the low voltage and the medium voltage, we will call it as a power factor correction, whereas in the high voltage and the extra high voltage, the same thing we will call it as a reactive power compensation. So you need to decide whether you need 50 MVAR capacitor or 50 MVAR reactor or 63 MVAR, 80 MVAR or 125 MVAR shunt reactor to compensate the reactive power requirement. And sometimes this reactive power compensation requirement could be the combination of both, means combination of the reactor as well as the capacitor. Okay, for this, the best example is the metro. The combination, reactive power compensation, the combination is the example is the metro. Why? Because suppose if you take the metro or a traction, so what will happen when there is a train which is running, the demand will be more. By the time the power factor will be lagging. So that time, that means when the train is running, when the train is running, so you need the reactive power requirement. That means the power factor will be lagging. The power factor will be lagging. So that time you need the leading power compensation or leading compensation, you can say. Okay. On the other side, after the train is stopped, maybe by 11 p.m. or 12 p.m. or whatever it is, the network behaves as a cable. That network behaves as a completely capacitance circuit because of the cable, right? So that means it injects reactive power into the system. So that time you need the inductive when the train is stopped or when the metro is completely stopped. So that time, due to the cables, it will inject the reactive power to the system. So that time you may need the lagging compensation, or you will call it as an inductive compensation. Okay, so that's why essentially you need to consider the compensation requirement in both lagging as well as leading. So that is about the reactive power flow. So reactive power flow is mandatory because of the power factor corrections and because of the reactive power compensation. Okay, and of course, you need to think of the loop flow also. Loop flow is predominantly when you have the multiple generators connected to a common bus. That's what we have explained here. When we have a multiple generators and all these multiple generators are connected to a common bus, because of the voltage mismatch between them, there is a reactive power flow, which is like some generator will generate the reactive power and the other generator will consume the reactive power. So it really increases the losses and increases the temperature. But it is not doing any other activity because the reactive power is flowing just within the generators. It is not going to the load, right? So that's why it will cause the increasing, it will increase the heating effects. So that's what about the reactive power flow. I hope reactive power flow is clear. Yeah, reactive power flow is clear. So this is the reactive power flow. I think this is clear. Right. Yes. Any questions?
Sir, why we are connecting reactive power flow will be required, sir, in the system?
No. See, reactive power. I didn't get your question. So you're asking about why the loop flow?
Yes, sir. Because we are the paralleling the generator, sir. At a time we need the both terminal voltage will be same. Right?
No, that's what I'm telling you. I think Harshil, right?
Yes,
Harshil, what I'm telling is, this is the loop flow will exist when you maintain the different voltage set points of the generator. Okay.
Yeah, sir.
So,
but physically possible there is like conditions. Parallelly parallelly connected generator be other not the same voltage, sir. Is it possible thing, sir? I'm asking like that.
See, exactly. See, if you take the case of a large generators, like in the megawatt capacity generators, so probably this 100% and 102% does not create that much of difference. Okay. Because you have the reactive power limit. So there is a term called the generator capability curve, right?
Okay.
So if you see the generator capability of a large generators like 500 megawatt, 660, 800 megawatt generators. So you are having a capacity margin of minus 200 MVR, 300 MVR, something like that. On the lagging side, you have some 450 MVR also. So that means if the reactive power flow in the generator is well within the capability curve of the generator, there is no issue at all.
Okay, sir.
Whereas if you take the case of a 210 megawatt generator, okay,
Okay,
just
sir.
I will suppose 1 second, just give me 1 second. I will try to show you one simple example. Yeah. Yes. So if you see the capability curve of the generator, so this is basically the capability curve of the generator. Okay. So this is the capability curve of the generator. Yes. So if you see here, this is your leading side. That means in this zone, the generator is absorbing the reactive power. Whereas in this zone, of course, this I will discuss in detail when we are talking about the generator modeling, but just I'm giving some information about this. So this is the zone when you are delivering the reactive power to the grid. Okay. So this
Okay,
is
sir.
your active power and this is your Q positive, means you are delivering. That means your generator voltage is more than the grid voltage and you are pumping the reactive power from generator to the grid. Whereas this is the zone when you are absorbing the reactive power from the grid. Okay. Now, if you
Yes, sir.
see here, this is the blue line. So this is the generator capability curve. Okay.
Okay.
So that
Okay,
means
sir.
within this limit, you can operate the generator.
Okay.
Suppose if you are maintaining the, like two generators are operating in parallel, whereas this case, until and unless, let's suppose this generator is delivering more reactive power, correct? 21.42. So then what will happen? The reactive power flow, how it will be? It will flow from this generator to this generator,
This
right?
generator. Yes,
So
sir.
that
Yes.
means for one generator, the reactive power, that means the operating point will be in this zone, whereas for the other generator, the operating point will be in this zone, correct?
Okay,
Because
sir.
one is
Correct.
delivering and another is absorbing. So
Yes,
that
sir.
means for
A
this
loop.
generator, the operating point will be in this zone, whereas
Okay.
for this generator, the operating point is in this zone. That means until and unless you are operating the generators within this capability curve or the reactive power flow in the generators within the capability curve, there is no issue. Okay.
sir, understood.
Suppose,
Yes,
let's
understood.
suppose if I made this set point as 100%, suppose if I go to 90%. Of course, this will not happen practically, but still I am explaining you theoretically. Suppose the generator voltage becomes 18 kV. Then what will happen? There will be a heavy reactive power flow from this generator to this generator. So in
Like a
that time-
diesel. Yes, sir.
Exactly.
Simply
Your
like this
diesel
generator,
also-
like a load kind. Yes, sir. Simply tell that.
Yes. So in that case, for the reactive power flow, your generator acts as a load. Okay, but not for the real power.
Okay, sir.
Okay, in
Understood.
that case, it will act like not a particular induction generator. We cannot say if the completely excitation system is off, complete reactive power is taken from the grid, then we can say it as an induction generator. But yes, in this case, what it will do, this generator will try to maintain the voltage by taking the reactive power from this generator. Correct? So in that case, what will happen? Probably this generator may go beyond this operating curve.
Yes, sir.
Okay, so
Yes.
that will create when the generator goes beyond the capability curve and when it is operating outside the capability curve region, what will happen? There will be a core heating. End regions, at the end regions, because of this leakage flux, the core will get heated. Okay, and when it continuously when it continuously is operating within the zone, so what will happen? The core may get damaged. Okay, so that is what precisely I want to explain with this example.
Okay, understood, sir.
Clear, na?
Clear, sir.
Fine.
Thank you, sir.
Yeah. So I hope reactive power flow is clear. Next, we will go to the next one, right? That is, move on to the next one. That is defining the transformer tap settings. Next one is defining the transformer tap settings. So you need to identify whether on-load tap changer is needed or off-load tap changer is sufficient. Okay. If you found it is needed, if you found like OLTC is needed, then what is the maximum tap? What is the minimum tap? So you need to determine the both, right? What is the maximum tap? What is the minimum tap that is required? So you can decide this only based on the load flow analysis. And this also decides whether the entire reactive power capability of the generator, like what I explained here. So whether the entire reactive power capability of the generator could be taken out or not if there is a generator step-up transformer. Okay, so the purpose of finding the tap is just not to find out the OLTC range to regulate the voltage, while it is the range to extract the complete reactive power requirement from the generator. So let me note it down here. So the purpose of the OLTC range is not only to regulate the voltage. One purpose is to regulate the voltage of the bus to the bus which it is connected. And the second one is the purpose of this OLTC is to extract the complete reactive power from the generator. Complete reactive power from the generator. Right? In case, because if you come across the systems like the thermal power plants, whatever it may be, the generator voltage is, suppose if you see here, the generator is, let's suppose 21 kV. Okay. So, but this 21 kV generator will not directly connect it to the grid. Okay, because of the transmission losses. So what will you? You will put a step-up transformer, which you will call it as a generator step-up transformer. So what that will do? That will step up the voltage of the generator from 21 kV to the grid voltage. It may be either 400 volt, it may be 220 volt. And then it will be finally connected to the grid. Right? Now, in this case, the purpose of the OLTC or the OCTC for this GT is not to regulate the voltage of this 400 kV bus. So the purpose of the OLTC or OCTC in case of the generator transformer is to extract the maximum reactive power that is available in the generator. Okay. So for this, there is a book, I think you may probably find in means in the Google also. There is a good book called KR Monograph. This is a very good book. Okay. So in this book, they completely explained about the reactive power extraction from the generator. That is also the responsibility of the generator step-up transformer. That is the responsibility of the generator step-up transformer. Means the OLTC or the OCTC of the generator step-up transformer is the responsibility to extract the maximum reactive power. That means the complete reactive power available in the generator can be extracted through this OLTC or the OCTC of the generator transformer. Because most of the times we always think that the OLTC is just to regulate the voltage, but it is not the case. OLTC may not be able to regulate the voltage if you not have a sufficient reactive power. So that we have to look into, right? So OLTC may not be able to regulate the voltage if you do not have a sufficient reactive power, right? So that is about the transformer tap settings, which you need to find. What is the transformer tap range? Means what is the minimum tap? What is the maximum tap and the step size? So to determine all these things, we need to do the load flow, right? Next is the load flow gives us the system losses. So that is the total losses as well as the individual branch losses. So next one is the system losses. So that means that is the total losses, which means the individual equipment losses, plus branch losses. Okay. So out of this, what we are going to take out is what should be the ideal configuration for normal operating conditions. So the purpose of performing the load flow analysis is to evaluate the all possible combinations until what is the configuration in which the losses are less. Right, correct. If losses are less, then that's the ideal condition. And it is not about the losses, it is about the voltage profile. It is about the equipment loading, and it is a combination of both. So what I meant by this is, let's take with example, let's take the same example what we have discussed yesterday. Suppose I'm having a transformer I'm having a transformer which is feeding the load to one particular bus, let's suppose. And there is a bus coupler and there is another bus to which wait, one second. Yes. Yeah. So there is another bus which is feeding to this, feeding by the transformer, and it is supplying the loads. For example, these are the loads, different loads are connected to this bus. For example, let's suppose. Now here what I'm talking about the configurations. Configurations means, see, this is one configuration, like that means here the breaker is closed, this breaker is closed, and this breaker is closed. That means individual transformers are feeding to the individual buses, and the bus coupler is off. And the bus coupler is off. So that means the bus coupler is open. Okay. So this is one configuration. So in that case, let's suppose the bus voltage profile is, let's suppose 98% is here. And the equipment loading, the transformer loading is, let's suppose some 70%. And here also it's 70%, considering both the same loads. And this is 98%, right? So this is the equipment loading and the branch loading as well as the power losses for one configuration, that is the normal configuration. So in the normal configuration, both the buses are fed by the individual transformers. Now take another condition which is called the contingency condition. Suppose let this breaker is out or this breaker is open and I close this bus coupler. So in that case, what will happen? Entire load will fed by this transformer. So in that case, the bus voltage profile will never able to meet at 98% until and unless you won't change the tap of the transformer. So if you are operating at the normal tap at which it was operating, so probably that time when you are feeding both the loads by this transformer, that time the voltage of the bus may come down to, let's suppose 95%. And of course, the branch losses will increase and the equipment loading may reach 90%, something like that. So that means you have to evaluate the different configurations. But in this case, what will happen? The fault current will be more. If a fault happens on this bus, the fault current will be more. Whereas if the individual transformers are fed by the individual buses, so the fault current will be less. So you have to look into the different configurations and to find out which configuration gives you the less losses, means less equipment loading, less equipment losses, branch losses and all. So you have to validate, you have to find out different configurations and you have to conduct the load flow for different configurations. And finally, you have to come out with a configuration so that in which your voltage profile will be better, equipment loading or the power losses will be less. So to evaluate the required configuration, you have to conduct the load flow. That's what precisely I want to explain with this. Okay. Yeah, clear? Yes. Yeah, is it clear? I think.
Yes, sir.
Okay, fine. Thank you. Next one is, yeah, here there is one more concept that is called the optimal power flow. When we are talking about these configurations, there is another term that is called optimal power flow. So, which is probably means the same. So the objective of the power flow is to convert the load flow. That's what we think. But the purpose of the optimal power flow is to optimize what are the parameters and why do we need the optimal power flow? How it differs from the conventional load flow? What are the constraints? What are the optimization parameters? We will see in the probably during the load flow sessions. Means when we are discussing about the transformer loading on different configurations, that time I will explain. So I'm just making you familiarize about this term that is called the optimal power flow. Okay. So finding out what is the minimum possible loss, what is the ideal operating condition, and that is also decided by the load flow analysis. As a part of that, the optimal power flow, which minimizes the reactive power compensation, which reduces the losses, which probably better utilize the transformer tap. And probably this optimal power flow also decides what is the generator or exciter regulator voltage set points. Because if you go through this example here, so to operate the generator well within the capability curve or well within the operating limit of the generator, what will be your generator or the generator exciter or the voltage regulator set point? How it will be? So to find out that, we need to perform the load flow. So here the purpose is to find out the generator, exciter or voltage regulator set point. We need to perform the load flow, right? So let's probably put this point where this optimal power flow is also applicable. Suppose if you have an industry like this, probably we will come, I will try to explain in our load flow sessions also, means when we are doing the load flow modules. Oh, that time I will explain you in a much better way, but yes. So the purpose here, we can say something like this. In the optimal power flow, through the optimal power flow, we can optimize the, what will be the generator set point. That means what will be the operating range of the generator set point, whether it is operatable, it is recommendable to operate the generator within the operating range of 95 to 100% to 105% or 90 to 100%, 110%. That can be defined through the optimal power flow. Okay. So this is obviously required, especially when you are having a cogeneration industry. See what will happen in the cogeneration industry. So there is always a problem of operating the poor power factor, right? So that time, if you increase the generator set up terminal point, what will happen? So you are adding some additional reactive power to your loads, right? So probably the power factor may be improved by improving the generator set terminal point. So that's we will discuss during our real-time example in our classes. But just this is one small example where this optimal power flow is needed. Okay, right. Yes, is it clear? If it is not clear, just let me explain in this way also. Like I'm not really sure how many of you have seen big thermal plants, some generators like 500 megawatt, 800 megawatt, 600 megawatt generators.
I think Venkatesh, that would be better if we go all this discussion taking a real-time project example, then it would might be easy to understand with other participant.
Yes. Okay.
So please start with real project load flow modeling and parallelly the conceptual discussions will going on.
Yes, fine.
Yeah.
So this is about the means the purpose of conducting the load flow, means what are the requirements, why we have to perform the load flow and all. So that is what we have discussed till now. Now let's start with the generator modeling. First we will discuss with the generator modeling because that is the first. First we will discuss about the bus. If it is so, first we will start with the bus. So once we clear with the bus, then we will go with the equipment modeling like the generator or the power bus, swing bus and all. So that time we will go through that. But before that, first let us start with the bus modeling. Let me start the E tab. So if I start with the E tab for the bus modeling, so probably there are different type of buses, especially 4 type of buses will be there. One is, let me open the software here. Yes. So I think, okay, some examples, no issue. So if you see here, so we have different types of buses. So coming to the bus modeling here. So let's start with the type of buses. Basically, there are 3 types of buses. One is the load bus. Second is the PQ bus. And the third one is the PV bus, or you will call it as a voltage control bus, or you will call it as a generator bus. Okay, that's what we claim. And the fourth one is the swing bus or slack bus, or you will call it as a reference bus. And these are the categories which we have in the power system. So the first one is the load bus, PV bus, voltage control PV bus, or the voltage control bus, or the generator bus. Then the third one is like swing bus or reference bus. So load bus and PQ bus both are same, or PQ bus. So we can say here, so control X, control Y, yes. Right. So load bus or the PQ bus, PV bus or voltage control bus, or generator bus. Then the third one is swing bus or slack bus or a reference bus. Now for these buses, what is known, what is unknown, which you need to identify. Why? Because see, this is the grid, right? The grid is connected to the bus. So this is called the swing bus. So this is called the swing bus. So if you go to the grid here, so here different operating modes. So in the swing bus, what are the parameters that we will give for the generator or for the grid? So that defines the bus. So for this PQ bus, if you see here, for the PQ bus or the load bus to which you have connected this one, so you will define the parameters P and Q. Okay, so that means for this load bus, what are the parameters that are known and what are the parameters that are unknown? So generally in power system, everything we talk about with respect to 4 parameters. One is the real power, second is the reactive power, then the voltage, and the fourth one is the angle, right? But let me add a few more parameters here also, like PQ, voltage, angle. These are the 4 parameters based on which the buses have been defined. Here, the P defines the P generation or P demand. P generation or P demand. And Q could be Q generation. Reactive power could be Q generation or Q demand, right? So this is not really like voltage generation. That is only the voltage here. And this angle is the delta. Okay. And there is nothing like generation voltage or demand voltage and generation delta or demand delta. So here we are just given it as a voltage and delta. Whereas for the real and reactive power, you have the generation power or the demand power. Similarly, the reactive power demand or the reactive power generation will be there. So if you take the load bus, or you will call it as a PQ bus, you know the real power generation and you know the reactive power generation. That means PG is known, QG is known. Similarly, you know the PD, power demand is known, and the reactive power demand, QD, is also known. So if you take any load bus or the PQ bus, if you take any load bus or the PQ bus, for that bus, real power generation demand and reactive power generation demand is known, which means even if a physical generator is connected to a bus and if the generator is operating in the, let's suppose in the MVR control mode, which means if you take the case here, let's suppose take a small bus here and connect a generator to this bus. I am connecting the generator to this bus. And suppose if I'm going to operate this generator in the voltage control mode. So in that case, what will happen? What are the parameters that are giving? That means in the MVR control mode, this means this is the basically called the PQ mode. So in this case, in the MVR control mode, you are defining the active power and the reactive power, or you will call it as a real power generation demand and the reactive power generation demand is known. Which means even if a physical generator is connected to a bus and if the generator is operating in the MVR control mode, which means you have already given what is the real power the generator has to generate. That means P is known, and you are giving what is the reactive power generation. Q generation is also known. Though it is a generator which is connected to the bus, but that is only a PQ bus. So that means if you connect the generator to this bus, so this is called the PQ bus. Okay. So logically, what you need to really understand is when the sources are there, real power and reactive power demand is known, then that is the PQ bus. Next, what is unknown for the PQ bus? What is unknown for the PQ bus? So these are the known parameters for the PQ bus. And what are the unknown parameters? That means the voltage and the delta. So these two can be calculated by performing the load flow. You know the parameters, active and reactive power. You have to find out the voltage and delta. Okay, so if you know the real power generation, real power demand, reactive power generation and reactive power demand, and you are trying to find out the voltage and angle of that bus, then that bus is the load bus or the PQ bus. Okay, next is the PV bus. So what is the PV bus? So this, okay, here the preferred mode of generator is the MVR control mode. So this is not only applicable for the generator, the same is applicable for the swing bus also, or for the grid also. Okay, now next is the PV bus. So the PV bus is also called as the voltage control bus. Here I have already mentioned you voltage control mode, you can say. So if you check the voltage control mode, let's try to see. Suppose if I am checking the voltage control mode. So now see what are the parameters that are known. That means you have to know the active power, real power demand, and you have to know the generator terminal voltage. Okay, so what are the known parameters for this PV bus? That means the PG, that means the real power generation is known, the real power demand is known, okay, and the voltage is known. And what you have to find out? You have to find out the Q and the delta. So these are the unknown parameters. So these can be calculated using this one. How it will be? First, let me disable all these things. I think some error I am getting it here. Right. Now let's suppose I am connecting a generator to this, for example, load to this. Let's suppose the load is 10 MVA and the bus voltage is, let's suppose, some 11 kV here. Okay. Here the voltage is 11 kV. Okay, right. So here, suppose if I am operating the generator in the MVR control mode, that means I have to give the, what is the, let's suppose the generator voltage is some 5 megawatt generator, and the generator terminal voltage, generator active power, real power generation is 5 megawatt, and real power generation is, let's suppose, 1 MVR. Okay, 1 MVR. So here with this you will be able to find what will be the voltage and what will be the, if you run with this, so you will be able to find out what will be the voltage and what will be the angle. So this bus is called the PQ bus. Similarly, if you operate the generator in the voltage control mode, so in this, what are the parameters that are known? That means the real power demand is known and the real power generation is known and the voltage is known. So obviously you need to find out the reactive power. What is the required reactive power? And that means this MVR is unknown, and similarly the angle is also known. So this angle is called the delta angle. Okay. So if you try to observe this, same thing here. If you try to observe this, when I am in the voltage control mode, only the voltage and the real power are getting highlighted, right? Whereas the angle and MVR will be calculated automatically. Okay. Next, suppose if you are in the MVR control mode, that means this is the PV mode. So what will happen? Your real and reactive power is parameters are known, and these two parameters will be calculated. That means the voltage and the angle will be calculated. So this is for the PQ bus, whereas this is for the PV bus. Okay, I hope this is clear. Next one is the swing bus or the swag bus. So in this mode, you know the voltage, you know the angle of the particular bus, and you will find out what is the real and reactive power flow. So what is the swing bus or slack bus? Here, real power demand of the bus could be known, reactive power demand at this bus could be known, voltage is known, angle could be known, but the angle at which we are assuming, is it 0 or whatever it may be the number, that is the reference for the remaining buses. So when you talk about the angle here, the angle of the swing bus is the reference angle. When we say the bus angle is 30 degree, let's suppose you have different buses and let's suppose this is connected to a transformer. And here, let's suppose this is the another bus. Let's suppose the bus angle is 30 degree. So that means this 30 degree reference to this swing bus. Okay. That means this bus angle has been shifted 30 degrees with respect to the swing reference or this reference bus. So that angle is known. And probably we can say like we are assuming or presuming this is the angle of the swing bus. And that could be predominantly 0. Sometimes you can have a different angle also. Anyway, that is not really going to make any big sense. Now coming back to what is unknown here. What is unknown here? You really do not know what is the real power generation and what is the reactive power generation. And when we say this, this is called PG and QG. Okay. So that's what we have mentioned here. So for the swing bus, what are the known parameters? That is voltage is known and the angle is known. Whereas the P demand, real power demand is known and the reactive power demand is known. What you need to find out? You need to find out what is the P generation and what is the Q gen. Okay. So this is about the different buses that are available in the ETAP. One is the load bus or the PQ bus. Second is the PV bus or the voltage control bus or generator bus. Third one is the swing bus or slack bus or the reference bus. Okay. I hope this is clear.
Yes, sir.
Yeah. Next, coming to the parameterization of the buses. So for this, let's suppose start with the bus here. So if you see the bus, so this is the first info page of the bus editor. So here you have to give the bus ID. What is the nominal voltage of the bus? And here, when you have given this thing, automatically this will be calculated. This load diversity factor, I will explain you later. So when we go to the simulation models, that time I will explain. And here you have to give what is the allowable minimum operating voltage of the bus. Okay. But remember, this limit will be validated during the motor starting only. Here you also can see allowable minimum bus operating voltage in percentage of the bus nominal kV for motor starting only. And it will check for how many cycles. Okay. So this is the voltage limit. And next is the phase voltage here. So when you give the voltages here, automatically it will calculate. This phase will be updated for the line to neutral voltage and the line to line voltages will be updated automatically, just giving the number here. So they will be updated automatically. Next, these are the load categories of the buses. Suppose if you see here in this, different loads are there. Like if you talk about the loads, you have especially the lump loads. If you see here, you have the JIP load, we can say that is the constant impedance, constant current, and the constant power loads, right? So how the load distribution will be, means how much constant power, how much constant impedance, how much constant current. So all these things can be, you will get all those details here. Next, these are not important. Yes, this is important. Coming to the rating of the buses.
This load characteristic shall be fed by us or it is automatically generated?
No. When you run the, so for this bus, suppose let's say 10 MVA are connected, right? So instead of that, we will do one thing. Let me create a small example here. And first, and let's suppose this is the load. And let's suppose this is 10 MVA transformer, for example. So why there is some problem with this? Okay, and let's suppose this is some 10 MVA transformer. The impedance, I am assuming it as a typical impedance. And let's suppose the load is, for example, let's say 5 MVA load. And here, from here, you can set it whether it is a constant power or constant impedance. So what I'm doing, I'm setting 50% constant impedance load and 50% constant power load. So that means out of this 5 megawatt MVA load, if it is operating at 85% power factor, the real power is 4.25, which is simple. VA cos phi and VA sin phi. And according to this, you will calculate the MVR also. So in this 4.25, 2.125, 50% is the constant power load and 50% is the constant impedance load. Now just run the load flow here. Let's see. Yes. Now if I go to the bus here, see, if you see here, so it will clearly tell you how much is the constant power load that is flowing through this bus, how much constant impedance load is flowing through this bus, how much constant current load. Of course, we are not given any constant current load. So that's why these values are showing 0, but we have segregated it as a constant power and a constant impedance load. So that's why both the values have been updated here. Okay, so when we run the load flow, automatically this will be updated. Yes, I think it is clear.
Yeah. What is the motor generator?
Which one? Yes. So here, like if you will connect any motors to this bus, so that will be updated here. Like suppose if I connect any motor here, let's suppose it is 200 means 300 kilowatt motor, for example. And for example, run the load flow here. Yes. Now say this bus. Here, if you see here, the motor 5, that means it gives you the details like what is the KVA load, KVA of the motor connected at this bus. That's what it will describe. Okay. So here, this is the load corresponding to the lump load or the static load. And this corresponding to, this displays the, gives the, what are the motors and the generators connected to this particular bus. Okay. So those details will come here. Clear, right? So next,
sir.
coming to this is the rating of the bus. So here you have the different options to select the standard, to select either the IEC standard or ANSI standard. But as far as our sessions are concerned, we were focusing clearly on the IEC. And here the type. In the type, you have the option to select whether it is an MCC, motor control center, or the switchgear or switchboard, or it is a panel board. The different options are there. You can select the type of the bus here. Okay. So this is required when you are performing, of course, to evaluate the bus loading conditions. For that time, this is needed. And the second most important thing that is required for this bus parameters is when you are performing the arc flash studies. Whenever you are performing the arc flash studies, so this rating of the bus is very, very important. Okay, because based on the parameters that you will select here, so these arc flash calculations will be evaluated and it will give you the what is your incident energy calculations. So basically it will use this parameters of the bus. So here that time you have to select whether it is a MCC or switchgear, what is the continuous rating of the bus, whether it is a 3000 ampere bus or 6000 ampere bus for 2000 ampere bus. So that is the continuous rating of the bus can be selected from here. And here the peak rating of the bus. So this generally we will not give it to you. Generally it is not required. And here arc flash parameters. So these parameters are required for the arc flash study. So you have to give the details of the switchgear, like what is the gap between the conductors, what is the gap between the conductors and the ground, just to evaluate the arc flash parameters. Okay. So that time you need to look into these details, and these details generally we will get from the manufacturers. Okay. Or you can use just by selecting, you can use the typical data also. But if you have the actual data sheets, so you will provide the actual data sheets here. Okay. So that is about the rating. And here, based on the values, so automatically the arc flash parameters will be calculated. When you are performing the arc flash studies, so that time these parameters will be updated. And this is the protection evaluation, basically to check when you are doing the relay coordination on the arc flash studies. So that time whether the bus will able to withstand, that means depending upon the fault clearing time, whether your bus will withstand for that duration or not, that can be evaluated with this sheet. Okay. And here, this is the harmonic load flow. Of course, it is not required as of now. So coming to the bus, one is the nominal kV is important. So once you give the voltages here, automatically the phase voltage will be updated automatically. And the second is the load, whatever the loads that you are connected at this bus. So that will be updated under the section of the load. So here, remember, so this will here, the lump load and the static loads will be updated. Okay. That means If you see here in the equipments, you have different loads. One is your induction motors, and this is the synchronous motor, and here this is the lump load, and this is the static load. This is the static load. So only lump load and the static load data will be updated under the load section. And the motors and generators will be updated. Whatever the motors are connected to this bus, that will be updated in this. Okay. And these ratings are not required for the load flow. But yes, these are required when you are performing the arc flash studies. So these parameters are mandatory. Okay. So this is about the bus of the bus section in the ETAP. Okay, clear?
Sir, which type of the load considered as a lump load? Sir, means like a
Sorry.
what is a means which type of the load considered as a lump load, sir? What is?
See, let's suppose in the 6.6 kV bus, of course, in the 6.6 kV bus, generally we will not go with the lump load. Let's suppose if it is a 415 volt bus. Okay. In the 415 volt bus, you have the motors, you have the feeders which are going to like lighting, welding, distributions, some other distributions also, right? So
Yes,
instead
sir.
of modeling all the loads here, suppose from this switchgear, let's suppose assuming it as a 415 volt bus. Okay. And from this 415 volt bus, let's suppose some 20 number of feeders, outgoing feeders are going from this 20 volt bus. Okay.
Okay, sir.
So one option is you model that entire 20 feeders on this bus, or the other option is you just model the motors and remaining all the loads which are connected on the bus, you will just lump it as and assume it as a lump load.
Okay, sir, understood.
Okay. So that is what the lump load. So here the static load will be almost the one type of the lump load, but yes, there is a difference between this lump load and the static load. Of course, I will explain you when we are going through the load modeling. Okay.
Okay,
So
sir.
here this static load is nothing but the constant impedance load. There are terminologies that is GIP loads, constant impedance, constant current, and constant power loads. Static load equals constant impedance load. Okay. So that I will
Okay, sir.
explain in detail when we are doing the load modeling.
Okay, sir, understood.
Yeah. Clear?
Yes, sir.
Right. So this is about the load means bus modeling. Next, if we talk about the generator, next we'll start this generator here. Right. I will explain the generator modeling also. So here, the operating mode I already explained you. That means depending upon the parameters that you know, which are the parameters that are known, depending upon the parameters, you have to select the voltage control, MVR control of the power factor. But generally, we will operate the generators in the voltage control mode only. Why? Because as I already explained you here, so your objective is to maintain the generator terminal voltage. So when you are giving the voltage control mode, that means you are giving the generator operating voltage. At which voltage the generator has to operate, that you are defining here. So accordingly, the generator will adjust its MVR, means the reactive power. Okay, accordingly, the generator will adjust its reactive power to maintain the voltage. So that's why the preferable voltage, the preferable control for the generator is the voltage control mode. Whereas in the MVR control mode, what will happen? You are giving the only the megawatt and MVR to be maintained at this bus. Correct? No? So whatever the parameters that we are giving here, so that means these are the known parameters, which I already explained you. That means this is the megawatt. Means suppose if it is a 10 megawatt and if it is, let's suppose 10 MVR. So that means it will try to maintain the 10 megawatt and 10 MVR at this bus. That means the generator will try to give 10 megawatt and 10 MVR to the bus. So it will not look into what will be the voltage that is maintained at this bus. So that's why in the MVR control mode, the biggest drawback is it may lead to the over voltage conditions also. So that's why preferably it is always run the generator in the voltage control mode. So that is about the operating modes. Next, coming to the rating here. So here you have to give the generator rating. Let's suppose it's a 10 megawatt or 20 megawatt or whatever it may be. And this is the rated voltage of the generator. This is the power factor, operating power factor of the generator. For the conventional generators like the big generators, the operating range is, the operating power factor is 0.85 lagging to 0.95 leading. Whereas if you take the case of a diesel generators, the operating power factor is 0.8. So that can be selected here. And the efficiency and the poles, of course, these are not having much significance, but yes, when you are doing the transient stability, so that time these parameters are required. Just to check validate the means variation in the speeds. And depending upon the control mode you have selected, here you have to give the known parameters. Like suppose if you want to give, if you give the 10 megawatt here, for example, so what will happen? Yes. So suppose here, if you see here, when I am giving the generator voltage 100% and the megawatt as 10 megawatt. So, and I have given the power factor as 85%. So what automatically ETAP will calculate what is the Q maximum limit that can be maintained. How it will do? You know the MVA, you know the MVA of the generator, you know the real power, you know the power factor, so you can calculate the Q value. Okay, so that can be ETAP will calculate that automatically. Right. 1 second, I think. Sorry?
Some guys
Yeah. I'm just trying to mute all. So
And then he would click it.
where should I think? Yes. Yeah, fine. Right. I think now it's clear, right? Yeah. So here, depending upon
Yes,
the
sir.
values, whatever you are given here, by giving the, as I told you, right, when we give the power and voltage, automatically the Q and the delta will be calculated automatically. Okay, so here the Q is calculated. So in this case, what will happen if I run the load flow here? So that will try to give the 10 megawatt. Okay. So because the generator set point voltage, what you are given, that is 10 megawatt. Suppose if I say it to 5 megawatt, it will try to maintain the 5 megawatt. And the reactive power will vary depending, because you have given to maintain the 100% voltage here. So here the voltage is maintaining, the bus voltage is maintaining at 100%. So to maintain the 100% voltage, it will try to give the reactive power of 2.739 because you are keeping in the voltage control mode. Suppose if I keep in the MVR control mode, so what will happen? Let's suppose the generating should be able to give the real power of 5 megawatt, and let's suppose it will give the 6.2 MVR. That means entire reactive power I am pumping to the gray to this bus. So what will happen? Let's see. You are just telling to maintain the real power and the reactive power as per the predefined set limits. Now, if you run the load flow, see, it will never bother about the bus voltage. It will try to give the real power which has been set here as well as the reactive power which has been set here. Okay, so it will not bother about, it will not take the consideration of the bus voltage, whether the bus voltage is going beyond the limits or not. Okay, so that is the reason it is always preferable to operate the generators in the voltage control mode. Suppose if you operate in the voltage control mode, it will always try to, here you can define what will be the bus voltage to maintain. So it will try to maintain 100% voltage, and accordingly within the reactive power limit, yes, if it is able to push the reactive power limit up to this limit, it will push. Okay, I hope this is clear.
Yes, sir.
Yeah. Next is the capability. So this is the capability curve of the generator, what we have discussed here. So depending upon the data sheet that is available with us, that will be provided by the manufacturer. So we have to define the operating limits of the generator. So once you define the operating limits here, so while running the load flow or performing the studies in ETAP, if the generator is going beyond this capability curve, it will give you alerts here. So that it will try to know whether the generator is operating well within the limits or not. Okay. Next, coming to this is the impedance models. So these details, everything we will get it from the manufacturer only. So these are the different parameters: subtransient reactance, negative sequence reactance, zero sequence, transient reactance. So these are the parameters which are required for the transient stabilities. For the transient stability studies, these parameters are mandatorily required. And here you have the option to select the type of the generator and the type of the rotor. And here you have the option to select the exciter type, whether the turbine, which type of, what is the overloading capacity of the turbines, that can be selected here. And next, coming to the grounding here. So here you have to select whether your generator is solid grounded or it's a resistance grounded or grounding through a NGT, which we'll call it a neutral grounding transformer. So that can be selected here. Okay. Next is the inertia. So this is also required for the transient study analysis. So this we will get like what is the inertia constant of the prime mover, what is the inertia constant of a coupling gear and the generator, that can, those values can be entered here. So all these values will get it from the generator manufacturer. And here you can select the exciter model. So ETAP is having a vast library, as I mentioned you. So these are different models, exciter models, which are already built-in models, and you have the option to develop the UDM models also. Okay. Next, this is for the modeling for the governors. So different, almost all IEEE model governors are already available in the ETAP. This is for the PSS, which is the power system stabilizer. Of course, here in ETAP, we have only PSS 1A and 2A. But yes, there are different models are available in PSS like 4B, 5B, 6B, even 7B is also there. So if you want it, you can do the UDM also. And next, this is the harmonic. So if you have the harmonic pattern of the generator, so that can be given here. So this is the total protection, means basically these two are important. One is your I²T and that is the stator damage curve. So this is basically the stator damage curve is to limit the reactive power and to limit the generator fault current. Okay. And these are not important. So this is if you want to do any techno-commercial analysis, so that time this is needed. Otherwise, this can be not required. So this is about the generator modeling. I hope this is clear.
Yes, sir.
Yeah. Okay. So generator modeling and the swing bus modeling is almost similar. So there is no much difference between the generator and this one. Only the difference between the generator and this is for the, here the first page is same, the configuration is same. The configuration is same. And here you have to give the, for the grid, you have to give the what is the rated voltage of the grid. And here you have to give the what is the rated operating voltage of the grid. That can be given here. And this is the short circuit phase where you have to give the maximum short circuit current of the grid. So this you will get it from the utility and the X by R ratio of the grid. So if you know these parameters, like suppose the short circuit contribution of the grid is 40 kiloampere and X by R is, let's suppose it is 14. So automatically the short circuit MVA is calculated, which is √3 into voltage of this bus into short circuit kiloamperes. So that gives you the short circuit MVA, and correspondingly can calculate what is your positive, negative, and zero sequence impedances. Okay. Right. Next is the time domain. So this is also not required because if you want to connect this in the ETAP real time, so that time these things are required. Harmonics, this is also, if you have any harmonic profile, that can be related here. Okay. So this is about the grid editor. Yes, please.
Where we get harmonic value on all this value, where we get them?
If you these details, if you get it from the utility, so that will be better. Those details will be provided by the utility only. You cannot have your details. Right? So
Okay,
this,
okay, sir.
yeah. So
Okay,
this
sir.
is about the grid modeling. So for today, we will stop the session here because we have seen the modeling of the bus, generator, and the grid. Then in the next session, we will start with the transformer modeling and the load modeling. Then we will see with the different configurations how to create. Probably we will look into this data manager. Another 2 more weeks will be there. Means another 4 classes will be there for the completion of the load flow analysis. Because in the next class, we will discuss on the transformer modeling and the load modeling. And we will look into this database manager, how to create different views, how to create different configurations with some real-time example. And we will perform one load flow analysis for a typical project, and we will see how the report looks like and how to understand the reports. Okay.
Sir, can you just run a motor starter model? I'm facing some problem in that one. For the typical two motors, one is running and one is starting.
But this one, okay,
Yeah,
let's suppose,
yeah, I'm facing to integrate that one. So can you just help me on that?
okay,
So I can close my project.
okay, I will just explain you. Right. So
To
let's,
brief to select the that starter conditions.
yeah, I'm telling you just one second. Let's suppose this is the motor. Move it from the dumpster. Suppose there is a 5 MVA load has been already connected in this bus. So I'm switching off this one. And there is a 5 MVA lump load has been already connected. 300 MVA load is already feeding. And suppose if I want to start this motor. Okay.
Yeah. Yes,
So
sir.
for that, what you have to do, you have to go to the motor acceleration study. And before that, you have to give some parameters for the motor. So, okay, let me explain the motor modeling here parallelly. So the parameters that are required here, one is the ID of the motor and here to which bus the motor has been connected. Okay. Then here you have to give the MV kilowatt rating of the motor and the voltage rating. And once you give the parameters, so automatically ETAP will select this from the NEC library. The power factor at 100%, 75% and 50%. Similarly, the efficiency at different loading conditions. Okay. Then here the important parameter is to give the lock rotor current, which is called the starting current. So this is 650%. So this is generally we will have to give it as a 600% to 650%. So if you want to give it the IEC tolerance, that can be given, which is of plus or minus 20%. So you can give that IEC tolerance also. This is lock rotor current. And this model is for the dynamic estimation of the parameters. Like if you want to do the dynamic motor starting analysis, so that time you can use this. Anyway, I am going to explain when we go to the motor starting studies. And next, these are the inertia. This is also required for the dynamic starting, but static motor starting, this model and inertia is not required. And here you have to give the what is the accelerating time, no load starting time. Let's suppose this is 2 seconds and full load. Let's suppose the motor starting this time is 3 seconds. Okay. So
I was
this is
facing.
important for the static motor starting.
Yes.
And here you have to select the starting, like which type you are, means how you are starting the motor.
Okay.
Okay. YD starter. And here you have to select.
So can you get the standard? Yeah. So what is that voltage
Suppose if I
control?
want, yeah, suppose if I want to give the
I
current
have to
control.
I have to go with the star delta. I have to go with the YD, and I have to go with the soft
Yeah.
starter. I have to
For the
simulate
soft
also.
starter, you have the parameters, right? You
So
have the
this is a
control.
YD, na star delta.
Yeah, star delta is YD.
Uh,
So here you have to give, let's suppose it is give for 5 seconds.
okay.
Okay. Yeah. Star delta, this is, let's suppose this is giving for the 5 seconds. 5 seconds it will start. Okay. Now, to perform the motor starting, go to the study case here and create an event. Select it as a, let's suppose, the event ID is motor starting, and let's suppose it will start after 1 second, and let's run the simulation time for 10 seconds. So what will be the action element? The motor will start, right? So what is the motor ID here?
Motor
The
5.
motor ID is motor 6.
Motor 6.
Motor 6. And here you have to give the action starting category. So if you want, you can give it. Otherwise, you can, it is not required. Just means for the bus level, if you want to see here, you can give it. Otherwise, it's not required. Just run the motor starting analysis. Okay, wait. Short circuit, let's suppose this is 40 kiloampere and XPR is 40. Okay. And here, if you see the motor starting current, see. So here the starting current will be like this and it come down.
Okay. So how
Okay.
much it goes to 200%?
Yes, 200% of the full load ampere, because you have your starting
This
current
is in
is
the
650.
YD.
Sorry.
This is in the star delta.
Yes. So this is ideally the motor starting current is the lock rotor current where what we have selected is 650%, right?
Yes, sir.
As you are using the star delta here, so it has limited the starting current to near about 209%.
Okay, to the.
Okay.
Yes, sir.
So from there you can select the motor starting current and you can see what will be the motor starting current and all.
So next is the voltage dip.
Yes. Next is the voltage dip, means you can go to the bus voltage profile, or you can directly, instead of opening the plot, you can select, you can directly see here. You know the motor starting, you're starting after 1 second. So bus voltage magnitude and bus voltage percentage. So here you can see. So during the motor starting, the bus voltage is coming down to 96. Before motor starting, the bus voltage is 97.33, as you are already feeding the load here.
Okay.
Okay. During the motor starting, because of the star delta, there is a slight reduction in the voltage. Suppose
in the-
if you start the motor without any star delta, just let's see that.
DOL.
Yeah, if you start the DOL, none.
None.
Okay, and if I run, sorry. If I run the motor starting here, so see, 95.23.
Okay.
Okay, so you can see
So
the
can you just open the profile?
see.
This is 610. Yeah. 620.
Okay. So depending upon the voltage, simple. Why? Because this 619, it will be 650 ideally, but it is 619 because the voltage profile of the bus is 99.71, right? Before
Yeah.
starting the motor, what is the voltage profile of this bus is 97.33.
33.
So correspondingly, the motor current will come down.
Can we do these analysis in the Excel too?
Yes, 0.9733 into 6.5. So this will be near about 6.32. So that's what you are getting there. Because during the starting, motor will not act like a constant power load, it will act like a constant impedance load. So that's why that is the reason why you are using the star delta starter. Why the motor starting current is reducing, because it will act like a constant impedance load. So when you are reducing the voltage, automatically your starting current will reduce. So that will precise, no issue. We will discuss these details when we are doing the load modeling.
Okay, thanks, sir.
Okay.
I will try tomorrow.
Yeah, fine.
If any, but is there any Excel calculations for this one also?
Oh, you will get it in the Google, in the internet, you will get it.
No, I'm finding some problem. So any code which can refer that is just like IEEE 399 like that.
No, this starting is you will get it from the 60034 is one IEC document, you will get it. But
60034.
before, yeah. But the point is you may not get the detailed calculations.
No, I'll just check what is the requirement. So
Yes.
I want to check that all parameters in that one. That is static parameters.
Okay. That you can check.
Some message there, sir, from the survey.
Yeah, sure. Okay, right. So I'm ending the session for today. So tomorrow,
Fine,
next class, we will discuss on the transformer and load modeling. Then we will try out an example and we'll finish the load flow. Okay.
Sir, I have a doubt.
Yes.
Not from this class, actually, a general doubt, sir. Can you explain something little bit about this positive sequence, zero sequence, and negative sequence fault current? Just for understanding.
See, let me just explain you in this way. Like we have different type of faults. Like one is your types of faults. If you see, one is the positive sequence, right? Negative sequence. Yeah. Positive sequence. Next is negative sequence, and the third one is zero sequence, right? So positive sequence, you have the different type of faults. One is your phase to ground, phase to phase, LL fault, LLG fault, double phase to ground, and the triple L fault. Okay, three-phase fault. So the positive sequence will be always be there irrespective of the type of the fault. negative sequence will be applicable only for the rotating during the ground faults and the face-to-face faults, and the zero sequences will be only it will be for the ground faults only. Okay, so why it will be only for the ground faults? Because if you see the phasors of RYB, for the zero sequence, these three IR, IY, IB all are in the same phase. Whereas for the positive sequence, all RYB are 120 degree apart, and this negative sequence is 120 degree apart, but it is just opposite to that positive sequence. Like if the phase sequence is like RYB, for the negative sequence, it will be RBY. Okay. Whereas for the zero sequence, the phase angular difference between the three phases is 0. Anyway, I will touch upon this in detail when we are performing the short circuit studies, because if I start with this, it will take another 15-20 minutes.
I think
So
he
during that short circuit study, please.
Yeah,
I think
I will cover this.
sorry to interrupt. I think you want to know what is the meaning of positive sequence, negative sequence, and zero sequence. What is the conceptual in layman language? What is the meaning of
Yes,
this
sir. Yes,
sentence?
exactly.
See, one way I can say it as like the positive sequence components. See, why we are divided it into the positive, negative, and zero sequence components. That is first we have to look into. Right. Suppose if I have normally I have these three things: IR, IY, and IB. Right. So three phase currents are there. So when there is a fault, so the current IR will be different. Suppose if there is a L to ground to fault, phase to ground fault. So in that case, that IR will be different, IY will be different, IB will be different. Okay. So one option is you can calculate, you have to do some matrix calculations, and depending upon the admittance matrix and all, you have to calculate what will be the IR, IY, and IB. Second is for the simple calculation, they have gone with the sequence components, right? So this positive sequence components means the phase angular direction of this current IR, IY, IB. They are in line with your normal component, that is 120 degree apart. Suppose if you take your phasor diagram, it will be RYB. Correct? No? These are 120 degree lagging, 120 degree lagging, 120 degree lagging. Right? Now, so this is the balanced system. In the balanced system, the phase angular difference between IR, IY, IB is minus 120. Here it is 120 degree and 120 degree. Okay. Here the positive sequence is, it will maintain the same current, same phase angular as the balanced currents. Okay. So the component of the current which will maintain the same phase angular difference and the phase directions with the balanced currents, that is called the positive sequence current. If the currents will maintain the component of the current which will maintain opposite to this, that means here it will be B, here it will be Y. So that is called the negative sequence component, and the components which are almost in phase with this. So these are the zero sequence components. Okay.
So zero sequence come again. Zero sequence.
So that means the phase angular difference between the currents R by B. So that is 0. So they are the zero sequence currents. Okay.
Okay, sir.
Yeah. So that means because why this will be zero sequence, why we will call it as, suppose if a fault happens, the fault current will flow through this ground. That means all the currents will flow through the ground. That means it will be in the same direction. So that's why this component we will call it as a zero sequence component, and the phase angle difference is 0. Because they are equal in magnitude and phase in each phase conductor, they are having a phase shift of 0 degree with respect to each other. So depending upon the phase shift angular difference, we have segregated it as a positive sequence, negative sequence, and zero sequence.
Okay, sir.
Okay. Yeah.
Hi, sir. I have one doubt regarding ETAP report making.
Yeah. Okay.
In load flow analysis, I have different configuration I design, so I need to make it like a one report. How I can make it one report in all configuration?
So there you have to go with the scenario wizard. There is called a study wizards. So in this you have to add your whatever the load flow cases, and you have to run it.
Okay. Okay,
This
that's it.
anyway,
Okay.
I'm going to cover in our real-time example class. Because this is still pending. I have not touched upon this thing, right? This
Okay,
three-dimensional
because
database.
yeah,
So
yeah.
we will create the presentation view and configuration. Then we will look into the scenario wizard and the study wizard. So you will get everything.
Okay, because currently
Just
I
with
have
the suppose
yeah.
if you have some 10 cases and
Yeah.
if you want to run individually, so that will be a time consuming, right? So
Yeah.
for that, what we'll do, you can take the advantage of the study wizards and you can run all the studies in one single shot.
Okay, let's go. And report making also, right? Because I
Yeah,
have a project on
obviously, when
yeah.
you run this completely, so automatically the report will come in a single this one.
Okay.
Okay.
Okay then.
So
Okay,
you
thank
may
you.
use for this, you may have to use this the scenario and the study wizards. Yes.
Okay, thank you. Yep.
Yeah. Anything else? Anyone have any doubt to till the classes?
Thank you, sir.
Whatever we have discussed. If it is clear, we will end the session for today. And next sessions, we will discuss on the transformer modeling and the load modeling. Okay.
So that would be on the weekend only, Venkatesh, or any possibility if any schedule possible?
For me, actually, it is getting difficult during the weekdays because I'm quite busy with some important projects. So for me, it's becoming very difficult during the weekdays.
Okay.
Okay. Yeah. Right. Okay. I'm ending the session for today. And right, if you have any doubts, you can ask me at any time. Right. Thank you.
Okay, thanks, Venkatesh. Thanks for your time.
Okay. Thank you, sir.
Thank you.